Today we're taking a look at section 2.5, which is called Implicit Differentiation. And it's kind of an extension of what we've been doing with all the other things in this section. And it is a little complicated. So let me talk about first what it is. What we have been doing so far is called explicit differentiation. We can take a derivative of y in terms of x, and every single time we've had so far, we've had the opportunity where it's y on the left and everything else on the right, or f of x on the left or g of x or whatever. But the function name is on the left, and everything else on the right has the variable in it that is identified with that function. So sometimes it's not easy to have an equation solved for y. This is an example of one that you've seen before, but it's not impossible. It's still just not easy. If you think of the equation of a circle, we'll just use a standard equation. X squared plus y squared equals some number. Or if it's centered somewhere else, it has a little bit more going on. While you can solve for y, it's not easy because you end up having a plus or minus involved, and it just is ugly. Okay? Some equations are simply impossible to solve for y. So implicit differentiation is what we can do when we have a derivative of y in terms of x, but we cannot simplify it to say y equals, or doing so is complicated perhaps. In order to use this method, we actually treat both x and y as variables, and then we use all the derivatives that we've seen so far. So if you're thinking about the derivative of x squared and you know it's 2x, we have the same thing going on for y. The derivative of y squared would be 2y with one caveat that I'll show you as we work. Okay, but the basic idea is the same idea. So we're going to do some examples. Sorry, some of you are still filling in blanks. Let me pause. Of what this looks like. All right. This isn't an equation of a circle. Do you guys know what this is an equation of? Somebody remember it? It's a hyperbola. Very good. Yeah, it's a hyperbola. If you don't remember it, it's not a big deal, but that is what it is. We could solve this for y, right? We could. We can move everything. We can take a square root. We can put a plus or minus on it. It's doable. But it's actually a lot easier to do it with implicit differentiation. So let me show you what implicit differentiation looks like. Now, y'all know that the derivative of x squared is 2x. And I mentioned just a moment ago that the derivative of y squared is 2y. But I also mentioned that there was a caveat to that, right? There's one extra little piece that you have to know about that I haven't talked to you about yet. So it's 2y. That's true. But do you know that whenever we have our equations and we do y equals and it has all this stuff, and we take the derivative of y, we write down y prime equals, right? And another notation for y prime here that we're going to use in this section is dy dx. That's another notation for it. The derivative of y with respect to x is how we read that. So the derivative of y is dy dx. So when we see y squared, it's actually a chain rule. The derivative of the y squared part itself is the 2y. That's the outside of my chain. And then the derivative of y, that is the inside, whatever y itself is equal to if we were to have solved it, is dy dx. So every time we take the derivative of y, whether it's combined with something else or whether it's isolated, we get dy dx. And then on the right-hand side, the derivative of 25 is 0. Let me move this over. Now, we are going to solve this equation that we currently have here so that it says dy dx on the left and everything else on the right. We're going to simplify that. So we're going to move, I'm just going to move this whole piece to the left, to the right, excuse me. So 2y dy dx. And then what would I do to get the dy dx alone? My goal is dy dx alone. Divide by 2y. So dy dx is equal to x over y. Okay. Now, you'll notice that my derivative, dy dx, also has a y in it on the right. That's pretty common Doesn't have to be that way, but it's pretty common that when I do this, I still end up with an equation in terms of x and y on the other side. Okay? Now, if I were to go further, if I were to be finding a tangent line, if I were to be given a coordinate x, y, we could actually plug it in. And it's actually really nice because in your book, they like to tell you at the point, and they give you an x and a y. And so far up to this point, we just have plugged in x. Well, now we have the x and the y to plug in when we're finding the derivative at a specific location, which we'll do later on in the lesson. Okay, so this is a very clean one to start with. They get messier pretty quick. There's a couple of things we could do here. We could treat this equation exactly like it is, and that's totally fine. And we could go forward and we could take the derivative on the left. We're going to have a quotient rule. The derivative on the right is going to look kind of like the last equation that we did, and that would be that. The other thing that we could do is we could multiply everything by y so that I don't have any fractions, which means there's no quotient rules. It will complicate the right-hand side just a tiny bit, because what it'll actually do is it'll make this piece times y, which means I'll have a product rule on the right-hand side. So you give a little, you get a little. I mean, it doesn't really matter. So let me just ask you what you'd like to see. Would you like to see us multiply by y or to leave y where it is? Yeah. I think it's a little bit easier to multiply by the y, and so let's do that, and then we can actually look pretty quickly at what happens if you choose to do it the other way. So if I multiply everything, of course, by y, I get x plus 3 on the left, which means its derivative is really straightforward. I have 4xy, so I do have a product rule here. And then I just have y cubed, which is practically the same as doing y squared, not any different in terms of computational. So if I've done that, the left-hand side's derivative is what? 1. On the right-hand side, I have two pieces, right? I have 4x, and then I have y. So I treat it like a product rule. Product rule says I leave the first piece alone, 4x. And then I need the derivative of y. What's the derivative of y? 1 dy dx. You don't necessarily have to have the 1, but if you want to write it as a reminder for now, fabulous. And then I flip it around. I need the derivative of 4x, which is 4. And then I just rewrite the y. Right, the second piece gets rewritten. And then I need the derivative of y cubed, which is 3y squared dy dx. Anytime I take the derivative of y where there's something done to it, whether it's a product or the chain or something, I have a dy dx that's going to come out. Now my goal is to solve for the dy dx, which means that these pieces with the dy dx need to be grouped together so I can factor dy dx out. This piece doesn't have a dy dx in it, so it's going to get booted to the other side with the 1. So the first step I'm going to do is I'm going to write this as 1 minus 4y. And then I have it equal to 4x dy dx plus, what do I have, 3y squared dy dx. Is that okay so far? Just shifted part of my equation. So in order to solve for dy dx, I need to get it alone. Well, right now it's in two places. The only way to isolate it then is to factor it out of both of those places. So I can take my dy dx. I've got 4x when I factor it out, and 3y squared. 1 minus 4y. And then what would I do to eliminate this 4x plus 3y squared? I think somebody said it. Divide it to both sides, yeah. So we'll divide it to get it to shift. So what was it? 4x plus 3y squared. So dy dx would equal 1 minus 4y over 4x plus 3y squared. Let me run through with you what happens if you decide that you would like to do it with the way it was originally set up. Yeah, we'll go with that. So if you leave it like it is, you have a quotient rule. So the quotient rule on the left-hand side says I do the denominator times the derivative of the numerator. So y is my denominator. My numerator's derivative is 1. Minus my numerator, which is x plus 3, times the derivative of my denominator, which would be dy dx. And all of this is over the denominator squared. That's what the left-hand side looks like. The right-hand side will give me just a 4 for the 4x part, and then I'll have 2y dy dx for the y squared part. So I'm not so much sure that the derivative part is any different. I mean, I do a lot of the same operations. Cleaning it up definitely will look different, though. I need to get dy dx alone. So that y squared that's in the denominator, I first need to get that out of the denominator, much like on the original one that I did, I got the y out of the denominator to proceed, right? So as I'm working with this, the first thing I'll do is to multiply by my y. So I have y on top minus, and I'm going to leave the x plus 3 grouped together with the dy dx because that's actually a little more helpful at the moment. And then I'll multiply the y squared, so I have 4y squared plus 2y cubed dy dx. Did I get on pieces moved right? Does that look okay? Okay, so just like on the last one, I need my dy dx's to be, grouped together. They've got to shift to the same side. So I'm going to move this 4y squared over here on the side with the y, and I'm going to move my x plus 3 dy dx over here on this side. Okay? So if I shift those around, I will have y minus 4y squared equals, and then I'll have x plus 3 dy dx plus 2y cubed dy dx. So at this point, it becomes quite like the other one where I've got the dy dx in both pieces, so I factor them out. So here's dy dx. And over here I have x plus the 3, and I have the plus 2y cubed. And then I would divide by the x plus 3 2y cubed to the other side. And that would equal my dy dx. I'm not going to keep writing anymore, but that's what I have. So you might look at that and say, that doesn't look the same, and I would agree with you. I feel like, I don't think we made any mistakes, though. I think that there is an issue of how we can simplify something that would get them to look the same, but they are equivalent answers. Top's almost the same. The x plus 3 has a difference to it.
I have a question.
Yes?
So whenever you move the y from the denominator, could you have done like the top times y to the negative 2? Done it that way?
You could have, but in the final answer, you still won't know a negative exponent, so I think you're still going to end up having to eliminate something and move it to a denominator later. Yeah. All right. Let's move on to a different one. All right, number 3, same directions as before. We're finding the derivative implicitly. I have x squared y squared plus 37 equals 4x on this one. So that first piece, I've got the x squared and the y squared multiplied, which means I'm going to have a product rule, right? So we have a product rule going on right here. So the product rule says I write the first piece down, x squared, and then I need to do the derivative of y squared. So what's the derivative of y squared?
2y dy.
Good. 2y dy dx. So I'm hoping by the end of our class session today that dy dx is just sort of an automatic. You're remembering it, okay? Then then I take the derivative of the x squared, which gives me 2x, and I leave y squared written alone. Plus derivative of 37, 0. So it's really easy in the middle of all the hard stuff to forget and just accidentally write down the 37 again. So just throwing that out there as a cautionary thing. Keep in mind that we still have all those other stuff going on like we did before. And then the derivative of 4x is 4. All right, so this one's actually really nice because the only piece that has dy dx in it is the very first piece. There's nothing else in there. So I don't have to like factor it out of anything or clean it up like that I have in the other two in any way. I'm going to move my 2xy squared to the other side. So I've got, I'll just simplify this. I've got 2x squared y dy dx on the left. And then on the right, I have 4 minus 2xy on the right. Xy squared, sorry. Then what would I do? Right, divided by 2x squared y. Now, I haven't made any issue of it yet because we hadn't actually had the possibility to do so. But when we do have the possibility to reduce, we will. And do you see that we have the ability to reduce this one a little bit? Yeah, the 2's. So all of these numbers are divisible by 2. So I will, in fact, divide them all by 2. So I have 2 minus xy squared over x squared y. So far, so good? Where did the 2x squared come from? I think you're seeing it from here. Is this piece? Oops. Is that the 2x squared you're talking about? Yeah. Okay. The next one has a trig function involved. It doesn't complicate anything any more than anything else, except that I want you to see that you could actually have another function, not just x and y being multiplied, which everything before we've had is more like that. This one actually has a chain rule because we have the sign, whoops, that has the x and the y embedded inside of it, right? But also, when I take the derivative of the inside xy, I will also have a product rule. Okay, so I have the trig rule on the outside, which is my outside function for a chain. And then I have the product rule happening when I take the derivative of the inside. So we'll start with the derivative of the sine. What's the derivative of sine? Cosine. And we rewrite the inside like it was. I was very pleased that most of you had that down really well on your gateway. And then we need the derivative of the inside xy. So what is the derivative of xy? Well, it's product, like I've mentioned. I've got the x, and then I've got the y. So I write my x first, and then I need the derivative of y, which is dy dx. And then I need the derivative of x, which is just 1, times the original other one, which is y. On the right-hand side, then, I have the derivative of x squared, which is 2x, and then minus 3 is 0. Okay, so this looks different than we had before. Namely, my dy dx is grouped by the x, but it's also somehow being multiplied by the cosine stuff in front of it, right? But there's addition inside where that dy dx is that I need to pay attention to. So what I've really got here is I've got this cosine of x that needs to be distributed to each one of these two pieces inside. And I really do have to do that. I can't just say, oh, well, let's just move something and then avoid doing that. It doesn't work like that. So I need to distribute that piece through. So I'm going to have the cosine of xy, and then I have x dy dx. I'm just going to write it in parentheses for the moment just to make sure we don't lose any pieces. And then I have the cosine of xy times the 1y or the y. Okay, that's my distribution. If you don't need to see it written, then don't write it. But I'm going to do it for now. It's going to look a little bit cleaner for us if we probably write this piece and this piece in front of the cosine, because I definitely don't want you to be tempted to multiply by the xy that's inside of cosine. So I'm just going to rewrite them in front of, so x dy dx, or if you want to write the dy dx at the end, you can, but I'll just leave it that way for now. Cosine of xy plus y cosine of xy equals 2x. All right, so my goal is to get the dy dx alone. So this piece that's the y cosine xy is going to shift with subtraction. So I have this first piece again rewritten. And it will equal 2x minus y cosine xy. What do I do now to get the dy dx alone? Yeah, so I divide by x because it's in front of the dy dx and cosine xy, which happens to be behind it. So dy dx equals 2x minus y cosine xy divided by x cosine xy. Now, I don't have anything to simplify here, but I just want to make mention that not only could I look for numbers, right, coefficients, I could look for variables. So there's an x cosine xy here, and there's a 2x here. If this said x cosine xy, we'd have the ability to reduce by x as well. So not only are we going to be able to reduce sometimes with coefficients, but sometimes also with variables. All right, so to continue our development like we have in the other sections, we're going to do the same thing we have done already with this next problem, but then it says on the end we're going to evaluate the derivative at the given point. So we have this additional step at the end where we're going to plug in the x, and at this time now often plug in y as well, because we often end up with our equation having an x and a y in it on the right-hand side. So we've got x cosine y. That's a product rule, right? So there's two pieces. So when I do the product rule, I write the first piece down. Then I need the derivative of the cosine of y. So what's the derivative of the cosine of y? Negative sine y dy dx, right? Okay, so again, remember, anytime you're taking the derivative of something with y in it, it's going to have a dy dx attached to it. Because what you really have is a chain rule. The derivative of the sine part, and then the derivative of the y part itself. And the derivative of y is dy dx. That's half of my product rule. And then I need plus, well, the derivative of x is 1. And then I rewrite the other piece, cosine of y. And what will it equal? 0. Okay, so this is a fairly clean one. Again, kind of like the last one where I only have the dy dx in one place. This one's even really nice because I have only the x. I mean, I don't have any addition or subtraction going on like I did over here where I had to distribute something through. I don't have any of that either. So if you would like to clean up a little bit, you can pull the negative through. So negative x sine y dy dx. And at the same time, I'm going to go ahead and move my cosine. So this will be negative cosine of y on the right. And then I'll divide by negative x sine y. Are they both negatives? They are. Cool. So I can actually simplify this one to addition. If you leave it as cosine of y over x sine y, that's fine. If you wanted to change cosine of y over sine y to write it as cotangent, good. You could do that. Leaving things as cosines and sines is often preferable, but it certainly doesn't mean that couldn't be changed. But this is a reasonable place for us to stop, right? If I was just finding dy dx. So dy dx equals cosine of y over x sine y. And I'll just put over here that, or you could actually write this as cotangent of y over x. That would be the equivalent if you changed to the trig function. But the directions wanted us to do this piece about evaluating. And this is the point at which we're evaluating. So x is 2 and y is pi thirds. So we're doing dy dx. And we're evaluating it at the point 2 and pi thirds. So that's how I'm going to write my notation to remind us that we're not finding dy dx in general anymore. We're plugging in a point. So x is 2, so that's right here. So I have the cosine of pi thirds over the 2 was positive, right? Yeah. And then the sine of pi thirds. Okay, so we're going to all tax our brain just a little bit to try to think about what happens on the unit circle at pi over 3. You need to know what the sine value is, and you need to know what the cosine value is. All right, so one of them is 1/2, and one of them is square root 3 over 2. Which one's which? Okay, so if you're trying to remember and you're like, because I mean, even as you're saying it, you're like, I think. So I always have to actually think about what's happening. So pi over 3. So pi over 6 would be here and pi over 3 would be here, right? Okay. So this location right here, is the x value bigger or is the y value bigger? The y value is bigger because I'm taller than I am to the left, right? So x is bigger than y. So this is the point 1/2 and then square root 3 over 2. That has to be that location in that order. X is the, whoops, I didn't mean to highlight that. X is the cosine value and y is the sine value. So as I'm looking at my exact expression now, my cosine value, my dy dx that I'm finding, my cosine value as x is the 1/2. And then I've got this 2. My sine value as y is the square root 3 over 2. We're definitely not going to leave it like that. That's atrocious for many reasons. So first, I've got the 2's going out here. So I've got now 1/2 divided by square root of 3. So we could do several things. One thing that you might want to do instead of dividing by square root of 3 is multiply by 1 over the square root of 3. So I end up with 1 over 2 square root 3. But I'm not going to leave it like this because that's got an irrational number in the denominator. So if I multiply by my square root of 3, I end up with square root of 3 over 6. And I didn't say it, but let me just say it real quick. My 1/2 of my square root 3 over 2 was positive because I'm in quadrant 1. Make an observation of that. Any questions on that one? Okay, similar directions on the next one, but we have a little bit different too. It wants us to find an equation of the tangent line. So what we actually found on this problem over here is we found slope, right? We found the slope at the ordered pair 2 pi thirds. Over here, we're actually going to find the tangent line, which means we find the slope, and then we're going to use that slope in the point slope form to find a line. It says find an equation of the tangent line to the graph, and then graph the tangent line in the same viewing window. What is this an equation of? It is a circle, okay? So we're going, when it talks about graphing it in the same viewing window, your calculator is not going to be particularly helpful for this graph. I mean, because a circle is not a function. So putting it into the calculator, while it's possible, is not easy, and it's really messy. So we're going to take the derivative for starters. So there are some chain rules here, right? This is a chain rule, and this is a chain rule because I have something inside of something squared. And while we could square it and multiply it out, and you can do that if you wish, it's easy enough to just treat it like a chain rule too. So the derivative of x plus 2 squared would be what? So 2 comes down, I rewrite the inside to the power 1, and then the derivative of the x plus 2 is 1. Plus, I'm going to do the same thing here, 2. Yep, and then times 1. And dy dx. Yeah. Again, it's because my derivative of my y has the dy dx component. So we've got that on the inside. And it's equal to 0. Now, this does not ask me to solve for dy dx. Did you guys notice that? So if you really want to, I mean, more power to you, go right ahead. But it does not ask me to do this on this problem. So if you want, you can actually plug values in right now. So that's what I'm going to do. I've got the x coordinate 4 and the y coordinate of 1. So x is 4, so this is 2 times 4 plus 2, plus 2 times my y value is 1, so 1 minus 3. And then it's dy dx. So things collapse really nice and easy because I didn't have to find dy dx directly. So 4 plus 2 is 6 times 2 is 12, plus 2 times negative 2, so that's negative 4 dy dx equals 0. So I can move one of these and then divide. So negative 4 dy dx equals negative 12. What is dy dx? It's 3. Okay? So pay attention to what you're actually being asked to do. Sometimes we get in such a rhythm that we just keep doing the same thing over and over again. But sometimes you're not asked to do all that, and we weren't here. So I have my dy dx, and remember that's my slope. And I have a point 4, 1. So my point slope form, y minus y1 equals m times x minus x1. And all my numbers are beautiful on this one. So y minus 1 equals m, which is 3, times x minus 4. We'll simplify, clean that up. So this is y minus 1 equals 3x minus 12. And y would equal 3x minus 11. Okay, so far so good? So let's think about this in terms of a graph, at least giving a sketch of a graph of what this would look like. I think I have another slide. It's even got a grid on it. That's what happens when you're thinking ahead these days. All right. So we're going to draw our xy coordinate grid. If you'll remember this equation itself being a great equation of a circle, can you tell me what its center is? Negative 2, 3. And its radius, which is not very friendly, I should have at least picked a nicer number. What is it? Square root of 37. That's approximately what, just for reference? It's approximately 6. It's really close to 6. For the purposes of our sketch, we're going to sketch out basically 6. Okay? So we're going to get our graph drawn, and I need to have a center of negative 2, 3. So here's the center. And then I'm going to go out 6-ish in each direction, and by each direction I mean left, right, up, and down. So I have this point, that one, and that one. And I'm going to do my best to connect the dots. Okay? That's awful. Let's try again. Okay, it could be better, but it could definitely be worse. All right, and our ordered pair, it tells us, is at 4, 1. So 4, 1 should be, I don't know. I don't think I've got it drawn very well. I don't. Sorry. I've typoed this twice, and I'm not sure this is drawn well. It should have been 1, 4, so I screwed that up. I've written it down wrong. I'm sorry. Let's go back and fix it so at least the graph makes sense. This should be the point 1, 4. The only thing it's going to change is, actually it's going to change a lot, isn't it? Okay. What do I want to do at this point? All right. I don't have a way to fix this right now. Can you imagine what we would do next if I had had my ordered pair correct? We would plot the point, it would be on the circle, and the tangent line would be beautiful, and it would connect to it, and it would all look like great, right? All right, so we're just going to all say that was just not a good choice, right? Okay, but it would work. It would work with ones they're going to pick out for you. So we would have a tangent line that looks, and I'll just draw a tangent line in for kicks and giggles, something like that. But that's not the tangent line we have because it doesn't solve like that. I'll have to fix that one for later.
Wait, why is the point?
What's that? What's my problem? Well, here's my problem, is that the point 4, 1 is not on my circle. So the point 4, 1 would actually be right here, but that's not on my circle because the point, that's not even it, sorry. 4, 1 would be here, and it's not on my circle. So I can't draw a tangent line through that particular point because it's not on my circle to begin with. That's my issue, is that I've got up the wrong point. The point should have been 1, 4, and we could go back and we could fix that, but it's going to have to change everything we did from here down. It might not be. You're right. Yep, 1, 4 doesn't fix it either. I'll have to go find a point on my circle and fix it later. So, yeah, but their point they give you will be on your circle.
Okay.
It will. I changed it from something that didn't work either. So I had 4, 4 written down in my notes when I did it back in the day, the first time I did it, and it didn't work then either because 4, 4 is not on the circle either. So
Nothing's on the circle.
4, 3 would be on the circle, but then I get a vertical line, which is not very useful for like solving things. So, at any rate, let's go to the next one. Last example. This is something we have not done at all yet. Any guesses as to what that notation might mean? Yeah, second derivative. If you're familiar and like using that prime notation like we have been using, it's double primes. We actually read this as the second derivative of y with respect to x twice. That's how that notation is read, the second derivative of y with respect to x twice. So what we have to be able to do is what we did before. We solve the dy dx, and then we replicate the process. So we're going to do the dy dx for this one. It's a pretty straightforward, clean one. This is another hyperbola. So if I take this derivative, I have 2x minus 2y dy dx, and then it equals 0, right? We've seen this kind of an equation play out more than once. We've solved it as well, where we shifted everything, moved it on the same side. So my negative 2y dy dx will equal negative 2x, and then my dy dx will equal negative 2x over negative 2y, which is just x over y. Okay, is that all right so far?
So was like our first one.
Yes, very similar to our first one. You're right. So then what we're going to do is we're going to take this and we're going to take the derivative again. We have to have the dy dx isolated to do this, okay? So it is important that we get all the way to the end step, whereas on some of the other ones we could stop somewhere in between and evaluated things and so forth. But we're going to get to here. So when we take this derivative, the derivative, it's like we're doing this now on both sides, okay? So the derivative of the dy dx is the d2y dx2. That's what it is. That's the notation they're referring to. And then I need to take the derivative of x over y, which is a quotient rule, okay? So in our quotient rule, I have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. What's the derivative of the denominator? dy dx over the denominator squared. I'm going to clean this up, but do you see how the dy dx popped up again? Yeah. dy dx cannot stay there. That's not acceptable. I need my second derivative in terms of x and y only. But I know what dy dx is. What is dy dx? It is x over y, right? It's right here. So this dy dx being x over y can be evaluated in for the dy dx here. That's what dy dx is equal to in this particular problem. So this piece right here is equal to x over y. I think I was saying it wrong out loud. I apologize. X over y. So we're going to use that and going to clean this up. So I have y minus x times x over y all over y cubed. And we definitely need to clean that up. Squared. I'm going to get a y cubed in a minute. I'm just jumping the gun. I apologize. Yeah, it's y squared right now. All right, so I do have this little y right here. Yeah. So the easiest way to eliminate the little denominator here is to simply multiply everything by that little y. So if I multiply by y on each term, then I will end up having xy on the first piece. Sorry, not xy, y squared. Y squared on the first piece minus x squared. And then my denominator is the y cubed. If you leave it right here, it's fine with me. But there actually is one more simplification you could do. Can you see anywhere on the screen what y squared minus x squared should equal? Really close. Negative 36, yeah. So up here at the very beginning, if you don't see it, I'm not going to penalize you for not seeing this particular. You got to get rid of the do I dx. That's not optional. But getting rid of the y squared minus x squared, we'll deal with that, okay? But this one actually is a very nice form where I know what x squared minus y squared is. It's 36, which means y squared minus x squared is negative 36. So this one does clean up into negative 36 over y cubed, interestingly enough. And that's dy dx. I should have drawn that over there first. d2y dx2. I will take this for sure. WebAssign might not take it. It might make you force you to go back and look and see if there's anything else. I'm not sure if it will or it won't. Just for a thought on that. Any questions?
Will you count off if you use y prime and y double prime?
That's a good question. Thank you for asking that, Alyssa. No. So if you do not want to use dy dx and you'd rather use y prime every time you do it, you can do that. I've taught it that way before. Here's the issue that you need to be really careful of as a potential. So it's really easy to lose the y prime, and then it gets mixed in with all the y's. dy dx sort of stands out a little bit more starkly against the other pieces as being different. And so that's what I gravitate towards at this point because I think it keeps it a little bit easier to keep all the pieces as they're supposed to be. But if you want to use it and you're real careful with it, I don't have a problem with you using it. Yep. Okay, any questions? Okay, so quiz on Wednesday, 2, 3, 2, 4, and 2, 5. There is a quiz review, some sample problems if you'd like to do that in Canvas. WebAssign 2, 5 is also due. You might be looking at this and saying, well, there's like a 2, 6 showing up somewhere else in my stuff. There is. We're doing 2, 6 at the very end of the semester for some other reasons. So you don't need to worry about 2, 6. It's not going to be part of this particular exam. Okay? All right. I will see you all, many of you, in my office over the next couple of days, and otherwise I'll see you here on Wednesday.
So do we go to your office?